Greetings to all. I am Dr. S. Brinda, Department of Mathematics, Kamaraj College of Engineering and Technology. In this video, we are going to learn about the concepts of residues and how exactly find the residues at the poles. Before that, we will move on to the definition of residues. That is, let Z equal to A is an isolated singular point of f of Z. The coefficient of B1 of Z minus A the whole power minus 1 in the Lorentz series expansion of f of Z about point A is called the residue of f of Z at Z equal to A. We denoted as B1 is equal to residue of f of Z at Z equal to A. In the Lorentz series expansion, we have to find the coefficient of Z minus A, that is called residues. Okay. Now we will move on to the methods of finding residues. Actually, we have two kinds of poles, okay, simple pole and pole of order m. Different types of formula for finding the residues. First one, suppose if we have a simple pole, then the formula for finding residue at a simple pole is r equal to limit z tends to a, z minus a into f of z. The second method is let f of z equal to g of z divided by h of z, where g of z and h of z are analytic function at z equal to a. And another one more condition for satisfy for this formula, if h of a equal to 0 and h dash of a is not equal to 0 and g of a not equal to 0 are finite, then z minus a is a simple pole of f of z, and residue of that particular pole a is equal to limit z tends to a, numerator divided by differentiation of the denominator. Then we can go for the next formula, that is 1 by m minus 1 factorial d power m limit z tends to a, d power m minus 1 divided by d z power m minus 1 into z minus a the whole power m into f of z. So we have three formulas for finding the residues. Let us consider an example. F of z equal to z cos of 1 by z, and they asked to find the residue at z equal to 0. Okay, so we are going to find the residue at the point z equal to 0. If you want to find the residues, first of all we have to find the poles. But for this problem, we are going to find the residues by using Lorentz series expansion. For using Lorentz series expansion, how to find the residues? We have to expand the given function in terms of Lorentz series, then we can find out the coefficient of 1 by z, since they have given the point as z equal to 0. Okay, we know the formula for cos z, that is 1 by z square divided by 2 factorial plus z power 4 by 4 factorial minus etc. This is the formula for cos z. Okay, we are going to use this formula for this problem. That is z into cos of 1 by z can be written as 1 minus, instead of z they have given 1 by z. Okay, in that place you can substitute z as 1 by z. Then what will come? 1 minus 1 by z the whole square by 2 factorial plus 1 by z the whole power 4 by 4 factorial minus etc. Okay, after simplification we will get, actually we are going to multiply this z for each every term. Then what will come? Z minus 1 by 2 factorial into 1 by z plus 1 by 4 factorial into 1 by z cube minus etc. Which is a Lorentz series expansion in the neighborhood of z equal to 0. Therefore, residue of the pole z equal to 0 equal to coefficient of z power minus 1. As per the given problem, what is the coefficient of z power minus 1? Z power minus 1 is nothing but 1 by z. Okay, what's the coefficient? Yes, minus 1 by 2 factorial. 2 factorial is nothing but 2. Therefore, the final answer for the residue is minus 1 by 2. Okay, this is the way to find the residue by using Lorentz series expansion. The problem is they asked to find the residue of the given function f of z equal to z square divided by z minus 2 into z plus 1 the whole square at z equal to 2. Okay, here they asked to find the residue at a particular point z minus 2. First of all, we have to find the poles. How to find the poles? Poles are obtained by equating the denominator to be 0. Then we will get z minus 2 into z plus 1 the whole square equal to 0. Therefore, we will get two poles, that is z equal to 2 and z equal to minus 1. What is the nature of the given pole? Z equal to 2. The power of z minus 2 is 1. Therefore, the nature of the pole is simple pole. And the second point, z equal to minus 1 is a pole of order 2. Since the factor is repeated 2 times, that's why it's called pole of order 2. For this problem, we have two poles. One is z equal to 2 and another one is z equal to minus 1. Actually, here they asked to find only the residue for z equal to 2. So, it is enough to find the residue at z equal to 2. And the nature of the pole is simple pole. As you all very well about the formula, just now I have explained the formula. What is the formula for residue at a simple pole? Is nothing but R is equal to R for residue, limit z tends to a, z minus a into f of z. What is a here? A is a pole. Actually, we are going to find the residue at a pole z equal to 2. So, instead of a, you have to substitute 2. Then what will come? Limit z tends to 2, z minus 2 into f of z. What is f of z? The entire function what they have given. So, instead of that place, you can substitute the given function z square divided by z minus 2 into z plus 1 the whole square. This z minus 2 and z minus 2 will cancel. Then what will come? Limit z tends to 2 z square divided by z plus 1 the whole square. Okay. Next, we are substituting the limit as z tends to 2. Then the final answer for residue is equal to 2 square divided by 2 plus 1 the whole square, that is 4 by 9. So, we get the answer for the given problem. Residue at z equal to 2 is 4 by 9. Okay. Third problem, third example. Here they asked to calculate the residue of f of z equal to e power 2z divided by z plus 1 the whole square. Okay. As usual, we have to find the poles. The poles are given by equating the denominator to be 0. That is z plus 1 the whole square equal to 0. Then it will come z equal to minus 1. It is repeated 2 times. Therefore, the nature of the pole is z equal to minus 1 is a pole of order 2. For this problem, we are going to apply the formula, third formula. Okay. What is that formula? Residue at a pole of order m is nothing but R is equal to 1 by m minus 1 factorial, limit z tends to a, d power m minus 1 divided by dz power m minus 1 into z minus a the whole power m into f of z. What is m here? M is nothing but order. What is the pole of order? 2. So, instead of m, you can substitute 2. Then what will come? 1 by 2 minus 1 factorial, limit z tends to a, d power 2 minus 1. Instead of m, I have to substitute 2. Okay. That is d power 2 minus 1 divided by dz power 2 minus 1 into z minus 2 the whole power 2 into f of z. F of z is nothing but the entire function, that is limit z tends to (1 by 2 minus 1 factorial), limit z tends to a, d power 2 minus 1, that is 1, d by dz of z minus 2 the whole power 2 into f of z. What is f of z? E power 2z divided by z plus 1 the whole square. So, after substituting the value of m equal to 2, we will get 1 by m minus 1 factorial is nothing but 1 factorial. 1 factorial is nothing but 1. Then limit z tends to a. What is a? Minus 1. Since we want to find the residue at the point minus 1. Therefore, limit z tends to minus 1, d by dz of z minus of minus what? Plus 1, z plus 1 the whole square. Here m is equal to 2 and f of z they have given e power 2z divided by z plus 1 the whole square. Okay. Next, this z plus 1 the whole square, z plus 1 the whole square get cancelled. Then it will come limit z tends to minus 1, d by dz of e power 2z. So we have to differentiate this exponential function with respect to z for only one time. That is limit z tends to minus 1. The derivative of e power is 2z with respect to z is 2 into e power 2z. Afterwards you can substitute the limit as z tends to minus 1. Then what will come? 2 into e power minus z. Therefore, residue of minus 1 is equal to 2 into e power minus 2z. 2 into e power minus z. Okay. Next problem. Here they asked to find the residue at z equal to pi for cot z. Here they have given trigonometric function, that is cot z. Here we are going to use the second formula. What is in the second formula? What I have given is nothing but residue at a particular point z equal to a is equal to numerator divided by differentiation of the denominator. Okay, here I am going to use this formula. Cot z can be written as cos z by sin z. As usual, the poles are given by the equating the denominator to be 0. What is in the denominator? Sin z. Sin z equal to 0. The 0 can be written as sin n pi. Sin n pi is also 0. Therefore, the value of z equal to n pi, where n belongs to z, which are simple poles. When we substitute z equal to 1, what will come? When we substitute z equal to 1, we will get z equal to pi. Here we are taking this value of z from the integer, that is z for integers. Okay. When we substitute z equal to 0, we will get, when we substitute the value of n is equal to 0, we will get z equal to 0. If we substitute n is equal to 1, then we will get the value for z equal to pi and so on. But in this problem, they have asked only residue at the point z equal to pi. Okay, so it is enough to find the residue at a pole z equal to pi. Therefore, when we substitute z n equal to 1, we will get z equal to pi, which is a simple pole. Therefore, using the second formula for finding the residue, that is nothing but numerator divided by differentiation of the denominator at z equal to a. What is in the numerator as per the given problem? Cos z. Okay, cos z divided by the differentiation of the denominator. What is in the denominator? Sin z. The differentiation of sin z is cos z. Okay, at z equal to pi. Okay, cos and cos get cancelled. What will come? 1. Okay, so for all the singular points, we will get the same answer. Z or residue at a point is equal to 1. Okay, since this cos and cos get cancelled, for any kind of singularity, z equal to pi or minus pi or 0, any point, we will get the same answer, z equal to 1. I hope you all understand for how to find the residues and the concepts of residues. Thank you for watching. Thank you.